Okay, problem 21. Problem 19. Now we're doing problem 19. Okay, problem 19. Crap, I did this one on the board with her. All right, so what we're going to do is we're going to first dissolve the 5 grams into enough water to make 100 milliliters of solution. So we're going to start by saying 5 grams of cobalt nitrate. Does anybody have the molar mass of the cobalt nitrate? 178.95. Great. Okay, into 100 milliliters. So then we're going to go milliliters to 10 to the minus 3 liters. And then we're going to go grams, 178.95 to moles. So this is going to give us the molarity, right? Did anybody get that? No. Okay. So 5 divided by 100 divided by 178.95 divided by 1e minus 3. Okay, so that gives us 0.279 molar cobalt nitrate. Now, I'm going to take 4 milliliters of the stock solution. So I have 4 milliliters. Okay. And then I'm going to dilute it to water to give it 275 milliliters of a final solution. Now, once I take that 4 milliliters and I dilute it, does that change the number of moles that I've taken from that stock solution? No, not at all. Okay? How many grams of the nitrate ion are in the final solution? So what I want to know is how many moles of cobalt nitrate are in that 4 milliliters. And then for every 1 mole of cobalt nitrate, I have 2 moles of nitrate. And then for each mole of nitrate, I have so many grams of nitrate. Right? Does that make sense? So, since I know that my moles do not matter how many milliliters I have here, that does not matter. Whether I dilute it to 1 liter, 5 liters, 275 milliliters, it makes no difference at all, right? We're agreed? Okay. Milliliters to 10 to the minus 3 liters. So my molarity doesn't matter. I can use this molarity with this 4 milliliters. Everybody with me? So I'm just going to do that. I don't even have to go to the 275 because that's just plain silly. Because I took 4 milliliters of the original stock solution. Does that make sense? So my original stock solution is 0.279. Oh, sorry. Backwards. Is 1 liter. Is 0.279 moles. And that's copper nitrate. Now, for every 1 mole of copper nitrate, how many moles of nitrate do I have? 2. I have 2 moles of nitrate. Now I want grams of nitrate. So for every 1 mole of nitrate, I have 48 plus 14.01, which is 62.01 grams. Okay, so if I run this out, we're going to do a little bit of praying because I haven't tested this. I get 138. Oh, that's just plain not right. Oh, times, nope, oh, sorry, times 1e minus 3. I get 1.38. So I would take 1.36 because we're all kind of winging it here on the numbers. So 1.36, 0.136, 19. Please be right. It is. I'm happy. D. So I'm going to take the 4 times the 0.279, which is the molarity, because remember we rounded off here on the molarity. So we also rounded off here. We're also rounding off here. So 0.279 times 2, 62.01, and that gives me 1.138. Plus, the other thing is, don't forget, if they had gone out to the 2.75, they might have gotten a different answer. Well, if they had taken 4 milliliters and then dilute this to 275, so they would then be using M1V1 equals M2V2, right? And so their first molarity is 0.279, 4 milliliter volume, and then their second volume is 275, and then what's your new molarity, and then you're going to go out and but you don't have to do that. So we might be off by 0.02. It's possible, because we're taking just the 4 milliliters, which, as I said, your moles aren't going to change, right? Your moles aren't going to change if you dilute it to 275 milliliters, or if you dilute it to a liter or 5 liters. That doesn't change your moles of copper nitrate. It doesn't change 1 mole to 2 moles. It doesn't change anything for the moles that are in that original 4 milliliters. It's going to change your rounding off, though, right? So you might end up at 0.002 off. Okay? Questions? Okay. Any other questions? Pausing. All right, so now we're doing number 22. So in number 22, what we're looking at is the number of ions. All right, so let's take something simpler than this that we are more familiar with. So if I have sodium chloride, that's going to dissociate into, that's going to dissociate into sodium plus chloride. That is 2 ions, all right? So if I have a 0.10 molar solution, I'm going to take 0.10, which is the number of moles in 1 liter. For every 1 mole of sodium chloride I have 2 ions. So I'm going to multiply that by 2. That means that I have 0.20 ions, molarity of ions. Yeah? Everybody okay with that? Because for every 1 mole of sodium chloride, I get 2 ions. So that means I now have 2 moles of ions per 1 liter. Okay? Now, if I were to double the number of ions per liter, I would double the what's the word? Thank you. The electroconductivity, right? Because that much more electricity could be passed, conductivity could run through, right? Electricity could run through the water because there wouldn't be that many electrical ions running through, which would facilitate the electricity to run through it. So in other words, the higher the number of ions in the water, the more electricity can run through it. So that's what I did. I said, this one is going to go into lithium and fluoride, 2 ions. So 2 times 0.15 gives me 0.3. 2 times 0.15, sodium and iodide, gives me 0.3. 2 times 0.1, lithium and bromine, gives me 0.2. Now this one, ammonia, and carbonate. Okay? So 3 times 0.04 gives me 0.12. But this one, aluminum and sulfate, gives me 5 ions. 2 aluminums and 3 sulfates. So that's 5 times times 0.045, and I get, it still works, 0.225. It doesn't work, does it? No, it doesn't work. It doesn't work, Miss Paxton. So then it would have to be -2, -6, +2 is -4, 0, 0, 0, -2, +2, nope, -6. Okay, well, I give up on that. Times 5. Well, I'll get back to you on that. Because I was positive that was it. I'll get back to you on that. No. It's not on the test anyway. No, I wouldn't do that to you. I'll get back to you. All right, moving on. Yes, so this goes back to solubility. So where's one of those? Yeah, so let's look at number 25. So 25 is ethanol. This is a carbon compound. Remember we talked about how sugar cannot be pulled apart, so it can't make those positive and negatives. There's no ions in sugar. It's a carbon compound. Well, ethanol, C2H5OH, same thing. Carbon compound, can't be pulled apart. Anytime you have an OL at the end and it's an eth or a meth or a di, right? And it's going to be a carbon compound, right? So it's going to be a non-electrolyte because it can't be pulled apart by water. It just can't. There's nothing. So the best it can do is it can make a hydrogen bond with the hydrogen coming off of the oxygen, but it's not strong enough to pull apart the molecule. So it's just going to take the whole thing with it. She's going to pull the whole thing away from its friends, like away from the other ethanols that are bonded to it, right? So there'll be ethanols floating around, yes, but they will be in ethanol as a total compound. They won't be broken apart like the sodium chloride, because remember, when we were talking about the sodium chloride, we were talking about how it was a little bit like a terrible analogy, but an ice cube, where what was happening is the outer ions were being pulled off by those water molecules because the attraction to those water molecules was stronger than the attraction to the chloride and the sodium. Because the sodium and the chloride are bonded together not by intermolecular, by bonds the way these are, by electrons being shared, but by the positive and the negative charges. So if a stronger positive or negative charge comes up to it, it will be torn apart and it will leave. Okay, that's what it's going to do. But that's not the way this is. these are actually sharing electrons. And if they're sharing electrons, they can't be pulled apart just because something with a stronger charge goes by, which is ultimately what's happening when this hydrogen from the water comes up. Now, an electrolyte is about the fact that the water pulls off this chloride, and now this random charged chlorine is floating around with a negative charge on it. So when you're looking at these as electrolytes or non-electrolytes, what you're looking at is, will they pull apart and leave charges floating around? So the first ones you're looking at is those family 1s, family 2s, ammonia, nitrates, and acetates. That there are no exceptions. Those are strong electrolytes. There are no exceptions. They will dissociate absolutely, so they're going to be strong electrolytes. Okay? Acids with those will be strong electrolytes. Those strong acids on that strong acid list. Hydrochloric acid, whatever the molarity of hydrochloric acid is, that is the molarity of those ions. 100% dissociation. That's a strong electrolyte. All right? So same thing with like potassium chloride, 100% dissociation. Why? Potassium, there's no exception. 100% of it is going to dissociate. So when we look here and we're looking at which pair of this compounds is soluble in water, we're looking at those solubility rules. So sodium, no exceptions. Nitrate, no exception. That's an easy one because you know what? Heavy metal, that's going to be a solid, right? Potassium, yes, but cobalt sulfide, no. You have to know those solubility rules. All right? And in the bottom, lithium nitrate, absolute. Calcium carbonate, no. Know those solubility rules. If something is slightly soluble, it'll make maybe a little bit of an electrolyte, a weak electrolyte, maybe, but it's not going to be a strong electrolyte. Must be fully soluble. So the best electrolytes are going to be those without exceptions, 100% sent over to the other side. All right. So keeping going with this, which is considered a strong electrolyte, well, definitely not the sugar compound. No, no, no. Lead chloride, well, that's a solid. That's a precipitate. So that's not an electrolyte. Another, acetate. Yes, this is going to be a strong electrolyte, but it's a weak acid. This is a weak acid, so it's not really going anywhere. So, no. And this is a carbon compound. Methanol. Nope. So that only leaves this, which, by the way, ammonia and nitrate. See ya, everybody's going over. Okay? Okay, so now, number 28. What reagent could be used to separate bromine from this, whatever this is? I don't even know what this is. This is like a methocarbonate bromide. Okay, when it's containing both. So the answer to this is that silver nitrate, because silver bromide is a precipitate. So that's why. For 28. 28. So silver bromide will be the one to do it, because when they connect, it's going to drop out of solution, so nothing will be able to take it back. So that's going to be the best one to separate the bromine, because the silver bromide will take it and then drop out of solution. All of these will not take it and drop out of solution, or they'll be slightly less soluble. But because the silver bromide, with silver being a heavy metal, It's going to take the bromine and it's going to drop out of solution. Sit at the bottom. So nobody will be able to take it back, the bromine. Okay? Now, which is the following is a precipitate reaction? So we did say that a double replacement is a reaction if it's a gas, a liquid, or a solid. But it's only a precipitate if it's a solid. So although letter D looks like it could be, and it is considered to be a successful reaction because it has the water, letter C is the only precipitate reaction. Letter D is not a precipitate reaction because water as a liquid is not a precipitate. Am I answering questions? So A is not a double replacement, it's actually a single replacement. It's not a precipitate reaction, it's a replacement reaction. See that? So they didn't combine and precipitate. What happened was the zinc replaced the silver. Correct. A precipitate in specific, that's a good question, Chino. The precipitate is in specific two ions in an aqueous state coming together and making a solid and dropping out of solution. Okay, moving on to I have number 42 as a question, or do you want to keep going in order? Yeah, we'll keep going in order. Okay, on question 35. So this combined being an empirical formula problem. So the first thing I did was I found the empirical formula between the nitrogen and the oxygen. So I found the number of moles by assuming 100 grams. Then I found the number of moles of nitrogen and the number of moles of oxygen. I divided by the smaller number of moles, and I found my empirical formula was NO2. I found my empirical mass was 46.01. Next, I used PV equals nRT to find the number of moles of this compound. All right? So when I did that, I found that I had 1.77 times 10 to the minus 2 moles. Now, they told me that 1.63 grams of this compound would occupy this much, milliliters, temperature, and pressure. So I took that many grams and said, well, that's how many moles this is. So using that, I had 1.63 grams. It's like an escape room. It's so much fun. I took that many grams over, see, this is grams, over the moles that I just calculated. And that gave me 92 as my molecular mass. Right? It's just like an escape room, I'm telling you. Molecular mass. Except my daughter's not here to make me feel stupid. That's what happens in an escape room with my daughter. And then I took 92, divided by my empirical mass, and that gave me 2. So I multiplied my empirical formula, and I got N2O4. So much more fun without her because she's so smart. She just pushes you out of the way and does everything. She never gives you a chance. And then you get the key and the door opens. And the guy goes, all right, have a good day. And he starts resetting the room. So, how do you do these problems? Well, you think they want the molecular formula. So, first you think, so that means I need grams and moles. How am I going to get grams? Oh, wait, they gave me grams. So that means I need moles. Oh, wait, they gave me all of this. I recognize this information, PV and N, right? RT, so I need N. Oh, wait, I need the number of moles, right? How am I going to find that? I'm going to use PV equals nRT, right? And so you start to put the puzzle pieces together based on what you have. But you got to think in your head, they want me to find this, and then units, 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 units. Decide what units that they want, and then how are you going to get to those units? That's how you're going to solve 30% of the problems on the exam. What units are they looking for, and how are you going to get there based on what units they've given you? Okay, problem 42. So in problem 42, a gas bottle contains 0.450 moles of gas at, and then I did my conversion right here. That's what this messy writing here is, 730 millimeters mercury. So I have 730 over 760 right there. And then if the final pressure is 1.15 atm, how many moles of gas were added to the bottle? So what I did was I said, here's my first starting moles. I'm looking for my final moles, so N1 and N2. Here's my first pressure, right? 0.450 moles of gas at this pressure, so here it is. And then, converting to ATM, 730 over 760. And then here's my second pressure, 1.15 ATMs. So then I took my PV equals nRT. And I said, well, they don't want me to use volume R or T. They just want me to use P and N, right? Like Avogadro's law and all those other Boyles and Charles, right? So I just canceled them out. And then I moved them over so I could get ones and twos. So I said, so I'm going to move over the N. So now I have P1 over N1. And then I set it up on the other side. So P2 over N2. Does that make sense? Right? So now I have P1N2 equals P2N1. I solved for N2, P2N1 over P1. And then I plugged in. Now, when I plugged in, I solve and I get 0.539 moles. Okay, so that's fine. And then they asked how many moles were added to the bottle. So this is my N2, 0.539 moles. So the question is, how many moles were added? So I took 0.539 minus 0.450, and I got 0.888. And that's the answer, B. So you have to subtract. Okay, now, number 43 is using the formula PV equals nRT, and I'm going to tell you right now that it's all right here. Kelvin is additive, not multiplicative. That means that if I raise the temperature from 40 degrees Celsius to 120, I did not triple my Kelvin temperature. I want to be clear on that. Does that make sense to everybody? So I tripled my Celsius, but I didn't triple my Kelvin. And so the answer is E, because the only way is by lowering the pressure by a factor of 3 and leaving the temperature constant. That is the only way that your volume is going to triple. There's no other way that you can use this equation and triple your volume by adjusting your temperature, except because all the other ones adjust temperature and pressure. So if you adjust temperature and pressure, you're adjusting both sides. So if you multiply your temperature by 3 or you divide your pressure by 3, it's not going to work. All right? Okay, the last one that Gracie wanted was calculate the ratio of fusion rates of Cl2 to F2. The formula is the rate of F2 over Cl2, and then I put the is the inverse to the square root of the molar mass. This is the molar mass of chlorine over the molar mass of F2. Now, I could have flipped these, and when I did not get one of these answers. So I flipped them in the other direction, and then I got letter D. So just by the way that they are phrased, you kind of have to play with it and put F2 on top, and then the next time put Cl2 on top and see how it goes. So what this states, the way this works is fluorine is 1.7 times faster in effusion than fluorine. That's how that works. All right? So that's the formula, and this is called Graham's law of effusion, and it's in your notes. Okay? All right, I hope that solves any questions. And this 49 is the lightest one moves the fastest. So neon is the lightest gas. Decreasing rate of effusion. Okay. All right, I'm going to post these on Canvas.